Welcome back, AP Calc AB students. We are going to push on. We've been talking about cross sections. Let's continue to talk about cross sections because, after all, cross sections are the bomb. So, taking a look at now dealing with semicircles and triangles. So, this is actually topic 8.8, and you'll notice that I'm kind of splitting my time between two different examples. So we're going to finish up example one, just do parts B and D, and we'll take a look at a second example and pick up where we left off after we finished part A in the previous video with parts B, C, and D. So what's going on with semicircles and triangles? Well, first of all, if we return to the first page of the notes, we already did a little bit of work here, and we finish up by finding our required information about a semicircle. So in other words, if you want to work with the formula for volume of cross sections, which we learned in the previous video, is just integrating the area A. And notice you can do that either with respect to X or Y. It all depends on where the cross sections are perpendicular. So we need to know area of these shapes, but before we know the area, we need to know some special information. So for a semicircle, what is that special information that you ask? It would be the radius, right? You can't do much with finding the area of a semicircle unless you know the radius. And so the formula for a radius, or for a semicircle, is 1/2 times our good friend pi r squared. And if you're wondering, why are we using semicircles? Wouldn't circles make a lot more sense? I love that question. Circles is basically going to be the rest of Unit 8. We're going to focus on those kinds of cross sections, and we kind of tackle them just a little bit differently, so stay tuned for that. Now, for the triangles, we need to know really a couple of different things. We need to know a base that I'll just call B, and a height that we'll call H. And of course, hopefully you recall from previous geometry courses that the area of a triangle is 1/2 base times height. Now, I'm going to put a little star by the triangle, and I just want to warn you ahead of time. The triangle is going to be the most challenging shape. And the reason is because there are very many different kinds of triangles. We could have isosceles triangles. We could have right triangles. We could have equilateral triangles, and each one has a bit of a different wrinkle. And so we'll have to focus on those here in this video. So if you remember from example 1, part A, we started with the situation where we had our enclosed region bounded by these three graphs. There's the sketch. And we found that the representative length here across the top to the bottom had a distance of 2 minus x. Now, when we go on to do part B, what we have to realize is that we are now concerning ourselves a little bit more with radius. We don't want the length of a side for our semicircle. And so it becomes vitally important that we realize that only half of this distance is going to be our radius. And again, you could think of that semicircle as kind of coming out at your face like that. Not a great representation, I get it. But if you can imagine that, that could be helpful. But what's more important is if you can imagine that the radius is half of the distance s. That's going to be vital. And so what we have here is that r is 2 minus x all over 2. Now, how does that manifest itself in our formula? Well, we're going to notice then that area is 1/2 pi times 2 minus x over 2 quantity squared. If you want to simplify that, I highly encourage it. You would end up with pi, the 2 here and the 2 squared in the bottom there, multiply forces and become 8, 2 times 4, and then you have 2 minus x quantity squared. And that is the formula for your area that you're going to find inside of your integration expression. We'll integrate again from 0 to 2. We have our pi over 8, and then the quantity 2 minus x squared with respect to x. So again, pi, 1/2, and the r squared all simplify to this expression. Now, I don't like to reinvent the wheel. So if you take a look at your part A, do you remember what we integrated up here? Does this look familiar? Whoa! It certainly looks familiar. In fact, the only way that our answer in part B is going to vary is by this constant pi over 8. So we're going to borrow our answer from part A. By the way, it was 8/3. And if we multiply that by pi over 8, we will get our answer and save a whole lot of time. So it's nice if you're working on a family of problems where they all begin with the square, because you can borrow that work. Sometimes these problems might be standalone. Maybe it's a multiple choice question that just asks for semicircles only, and then you'd have to kind of build it from scratch. But if you have them in a family like this, don't work any harder than you have to. All right, let's push on to part D. Remember, we did part C in the previous video. Now our cross sections are perpendicular to the x-axis and they're equilateral triangles. And so this is where things get a little interesting, because for an equilateral triangle, we need a couple of pieces of information. We need a base and we need a height. The base is certainly going to be the length from the top to the bottom. Now, how do I know that? Well, let me show you what's going to happen here. Picture this equilateral triangle coming out at your face. And I'm going to pick up that triangle, if you don't mind, and I'm going to set it flat right here. I'm going to set this triangle flat, and I'm going to try to use even the same coloring. Let's see if I can use the same coloring here, that purple along the bottom, because I want you to know that that purple along the bottom is what we called S, right? And this is the part that's like coming towards your face, right? If your face was up here. Now, this S is really the same as our B, right? I can call it the same thing, B. And I know its length because we worked very hard in part A to find that it was 2 minus x, top minus bottom. The height is a different story. The height is that length. And we need to figure that out. And we also need to use some really important geometry ideas to make that happen. So I'm going to take this triangle that's made right here, and I'm going to extract him from the picture and get a little bit better look on him, right like this, where this is the H. And now that I've dropped this altitude down, an altitude in an equilateral triangle will split the base in half. And so that base that was 2 minus x is now 2 minus x over 2. What else do we know? Well, this is an equilateral triangle, so that's a 60-degree angle. This is a 90-degree angle, which means that this must be a 30-degree angle. Or you could think about this altitude also bisecting that 60-degree angle. Now you have the stage set, as long as you remember this very important idea about 60, 30, and 90 triangles. A lot of kids tend to forget this, but I think that this is a must remember from your high school mathematics. Those are the ratios of the three sides. If the short side is 2 minus x over 2, then the hypotenuse is just going to be 2 minus x over 2 times the square root of 3. Now we can import that into our h, and things are going to start happening, folks, because we know that the area of a triangle is 1/2 times the base times the height. Let's get in the siding. And then we start cleaning things up, and look what happens. We have square root of 3 moving into the front, 2 times 2 move into the front in the denominator, and I see 2 minus x multiplied by itself and being squared, and I got to thinking, have we seen that guy before? And yes, we have. So the volume is just the integration, once again, from 0 to 2 of root 3 over 4 times 2 minus x quantity squared dx. And as I've said before, we're not going to reinvent the wheel. If we've already integrated the 2 minus x squared and got this 8/3, This radical 3 over 4, the square root of 3 over 4 is nothing more than a constant that just multiplies out in front. And so our final answer would be 2 square root 3 over 3. And there you have it. That, folks, is how you get the answer without reinventing the wheel. All right, let's move on to our problem 2. Now remember, the stage was set in the previous video. We were working on uh, a solid in which the base is the circle of radius 2. Remember, we changed the units to 2. We talked about developing this equation of the circle. We talked about how you had to solve it as a function. Whoop, I'm in the way. There we go. Right up there, we solved it just like that, plus and minus version. And then the top part is the plus. The bottom part over there is going to be the minus. And then we found our area using squares. Now we're going to do the same thing with semicircle cross sections. But remember, we know a trick. What we know is that the volume using cross sections that are semicircles is always going to be what again? Pi over 8 times r squared. Now, maybe we don't have that set. Maybe you're not quite sure, and that's perfectly acceptable. Maybe you have to get convinced. Well, if the radius is 2 minus x over 2, and if the area is 1/2 pi times 2 minus x over 2 squared, well, the only problem is where's this 2 minus x coming from? That's the previous problem, right? But it's the same idea. Let's do it the right way. This happens to be the length of S. So we would say that the radius is our side divided by 2, which in this case is 2 square root of 4 minus x squared over 2. And then the 2's just cancel, right? And so that's the radius. Therefore, the area is 1/2 pi times all of this square root squared. Well, look and see what happens when we put the volume together. We're going to end up integrating from -2 to 2, and the 1/2 pi would normally have come out in front. It's pi over 2, and we're going to square 4 minus x squared, which is 4 minus x squared. We're going to square the square root of 4 minus x squared. Now, I know you look at this and you think, well, wait a minute. This is not looking quite like what we did before. Well, I want to kind of clue you in on something. In this particular problem, you had a 4 that was hanging out in front, right? We don't see that here. Well, let's keep pushing through and see how this works out. Now, if you remember in the previous problem, when we did this, we said we would rather not start our integral at -2. We like to use our best friend of 0, know that there's symmetry happening, and double that result. And I'm okay with that. I think we should still consider that approach. And I hope that that doesn't confuse you. And so this is what's going to happen. This is what we're going to integrate. All right, so let's go ahead and make this happen. 2 times pi over 2, we could actually go ahead and cancel the 2's. Integrate 4, we get 4x. Integrate x squared, we get x cubed over 3. And then we have our boundaries of 2 and 0 that luckily we don't have to worry a whole lot more about because of the 0 helping us. Finishing up, pi drops in. 4 times 2 is 8. 2 cubed over 3 is 8 over 3. By the time we reduce this, we end up with 24 thirds minus 8 thirds, which is 16 thirds times our pi. And we could rewrite that a little prettier. And this is our answer. But wait a minute, time out. Wasn't our answer supposed to be pi over 8 times our previous answer for squares? We'll check it out. What is pi over 8 times 128 thirds? Well, let me help you out because the 8 goes into 12 one time. With 4 left over, the 8 goes into 48 16 times, and you get 16 pi over 3. So if you saw that coming, you could have just multiplied this by by pi over 8 and been fine. Now, if the question wanted to see what is your integral setup going to be, well, then you probably would be better off writing that out. All right. Hopefully that helps. When you take a look at part C, we'll attack it in a very similar fashion. We're looking at equilateral triangles again. So again, we need to know base and we need to know height. Our base is always just going to be the length of this representative slice, which we called S way back in part A. And if you want to see the visual, there's nothing wrong with that. I'm going to take this impending equilateral triangle here and I'm going to lay it flat. I'm going to put the S on the bottom and then the other links would look like that. Drop down in altitude, and then we remember that if we focus on this as being half of that S, we'll divide B, which is the same as S, by 2. And so this part is only square root of 4 minus x squared. And then if you remember, our height is always going to be the square root of 3 times that, which I'll just choose to write like that. So here's our height. I could multiply the 3 in. I'm going to choose not to, though. So then our area for an equilateral triangle is our good friend 1/2 base times height, which means we can now go to the volume. Integrate from -2 to +2 of 1/2. There's our base, 2 square root of 4 minus x squared. Now remember, we're back to our original base, which is everything in this triangle, times our brand new height that we found. And lo and behold, what occurs is a little bit of a miracle. Our 2's will cancel. I get it. We could bring square root of 3 out to the front. And you know what I think I might do? I think I might multiply by a 2, and I will change my boundaries to go from 0 to 2 so I don't have to do as much work. And then if we multiply 2 square roots of 4 minus x squareds together, we just lose the square root. Now if we finish this up, and I know I'm kind of running out of room, so I'll use some space down here. 2 root 3 comes out to the front. Integrate 4, you get 4x. Integrate x squared, you get x cubed over 3. Throw in your 2 and your 0. I'm so glad that 0 is a boundary. And we have 2 square root of 3 times the quantity. Our good friend 8 minus 8/3 shows up again. And that would be 2 square root of 3 times 16/3, right? Remember, 8's 24/3 minus 8/3. And then I suppose if we kind of worked on this a bit, we'd get 32 square root of 3 over 3 as our final answer. Now, what did we say back in part A? What did we, or in example 1? When we were using the equilateral triangle, we said that our answer was just going to be the square root of 3 over 4 times our square. All right, let's see, did that work? Let's take the square root of 3 over 4 and multiply it by 128 over 3. And let me think here. 4 goes into 128. 4 goes into 12 3 times, goes into 8 2 times. And what do you know? It matches. So another quick way that you could always find an equilateral triangle if you already found the square. Multiply by square root of 3 over 4. Now, if we take a look at our last one, last couple of parts here, parts D and E, what we're going to find are things are a little bit more complicated because of the special triangles that we have. And so what I am going to do is I'm going to close the video off now. All right, and I know we had mentioned that we might handle part D, but you know what? I made an executive decision. I think you've worked really hard and I think you deserve a prize. And I want you to go to the cabinet, and I want you to get an Oreo cookie. I want you to get a Chips Ahoy. If you don't eat cookies, I'm sorry. But reward yourself because you really learned a lot about cross sections. But I don't want you to stay away from long, because I want you to tune into the third video, because we're going to take a look at the next special kind of triangle. So be sure to check it out. If you like what you're seeing, be sure to subscribe. And as always, study your calculus. We'll see you next time.